Hey everyone, so welcome back. Previously, we were talking about the idea of redox reactions. We know that reduction and oxidation were described in four different manners. Reduction means gain of electron to become more and more negative charges, perhaps to react with hydrogen gas and losing all the oxygen. Oxidation is the total reverse of it. So, oxidation is the loss of electron to become a plus charge, increase the positivity, to lose hydrogen gas and gain more and more oxygen around the atom or perhaps the compound. In today's video, we're going to be talking about the idea of oxidation number. Remember in the first video I mentioned that instead of charges, we'll be using another term in the upcoming videos, and that is oxidation number. So it's a charge on any element, charge on an element that describes the loss or gain of electron by that element or by it. Oxidation number could be of three categories. For any element, it could be very simply a zero oxidation number, it could be a positive oxidation number, it could be a negative oxidation number. So if it is a zero oxidation number, it is obviously for pure elements, because only pure elements in their pure elemental state are zero. For example, pure elements could be in pairs, in groups, or whatever, but as long as it is the simple single element, it's going to be a zero. For example, pure sodium, 0, pure iron, 0, pure copper, 0. Even for non-metals, for example, pure oxygen, a 0. For example, pure bromine, 0. Pure nitrogen, 0. Even if it's an element with multiple atoms, for example, O3, which is also known as ozone gas, 0. It could be P4, which is phosphorus, 0. It could be S8, which is sulfur, 0. So as long as the element is pure and alone, it's going to be a 0. Positive oxidation number means the element has lost electrons. It has been oxidized recently. It was made to lose the electrons. So positive normally oxidation number is applied on metals. For example, sodium with a plus charge, potassium with a plus charge, magnesium with a plus charge. It is also implied on other elements which are in compounds, but we'll see it shortly. So not to confuse you guys right now, we are just calling it positive oxidation number means loss of electrons. There's another thing called the negative oxidation number, which means gained electrons. For example, chloride with a minus charge, bromide with a minus charge, oxide with a minus charge, phosphide with a minus charge. There are other possibilities as well, but over here right now we are talking about the simplest ones. So positive oxidation number means loss of electrons, negative means gain of electrons, and 0 means it's a simple single element. If it's a single element, it's pure element, it's going to be always a 0. How do we find the oxidation numbers? So finding an oxidation number is very easy, but we keep making it more and more confusing. Finding oxidation number. So first rule is very simple. Pure element is a 0. Pure element is equals to 0 oxidation number. For example, if it's pure sodium, it's a 0. It's pure copper, it's a 0. If I've written Cl2, it's a 0. If I've written pure nitrogen, it's a 0. As long as it's a single kind of element, as a single kind of formula, single kind of symbol, it's a 0. Pure carbon is 0. Then the other step is perhaps in compounds. When you're talking about compounds, pure charges is equal to their oxidation number. So if I write the charge on something, it is the same as oxidation number. For example, sodium with a charge of +1 has oxidation number is equals to +1. Potassium with a charge of +1 has oxidation number of +1. The charge itself is the oxidation number. Bromide with a charge of -1, the oxidation number is -1. For example, nitride with a charge of -3, the oxidation number is -3. So if it's a single charge, for example, copper with a +2, the oxidation number is +2. Iron with a charge of +3, the oxidation number is +3. So no biggie over here. It's not a big brain movement. It's very simple. If I write the charge is the oxidation number. You don't have to worry about it. But the trick starts in step 3. So if I am talking about compounds have total oxidation number of 0. Now what does that mean? This is the point where we need to focus. Whenever I am talking about a compound, the oxidation numbers tend to equalize each other. One part of the compound tries to equal the oxidation number of the other. For example, let's try out an example. Let's say I'm talking about, for example, sodium chloride. I know that sodium belongs to group 1. It has a charge of +1. Chloride, on the other hand, has to be equal to the +1 so that it can balance it, it can counter it. Chloride has to be -1. For sodium, the oxidation number becomes +1. For chloride, the oxidation number becomes -1. Let's try out few more complicated examples. For example, if I am talking about potassium oxide, I know that potassium belongs to group 1. So it has a +1 charge, but there are 2 oxygens over here, so it's a +2 because there are 2 potassiums over here, and it becomes +2 as a total. Oxide has to be equally opposite, so it is -2. So for potassium, the oxidation number is +1. You write it for a single atom, and for oxide, the oxidation number is -2. You don't write it for a whole, you write it for a single element. For a single atom I'm talking about, for a single potassium. We never record the oxidation number for multiple atoms at once. It has to be very simple, very individual. For example, I'm talking about, let's suppose, tin tetrachloride. Now this is where the brain gets more troubled. Let's suppose if I'm talking about, I'll move it over here so that I can show the charges. Let's talk about, I'll make it blue. Yeah, I know that chloride belongs to group 7. It is obviously -1. I don't know about tin, but I'm very sure about chlorine. Chlorine is in a compound. It has to be -1 because this is what group 7 does. There are 4 chlorides, so it's a -4. Tin has to be the exact opposite of it, so it's got to be +4. If individual chloride has an oxidation number of -1, individual tin has to have an oxidation number of +4 to balance out the 4 Cls. For example, if I'm talking about FeCl3, we know that when Cl is in a compound, it has to be -1. There are 3 Cls, which means -3. Iron has to be +3 to counter it, so it becomes +3, and the Cl is individually -1. Again, we write individual oxidation numbers for a single atom, not for a whole group. You don't write -3, sir, because there are 3 Cls. No, we just write it for a single Cl. Let's try out few more complicated examples. Let's suppose I'm talking about Al2O3. Now I'm very sure about oxygen. Oxygen is a -2. How many oxygens do we see over here? So it should be 3. There are 3 oxygens over here, so each oxygen is a -2. We see 3 oxygens, which becomes a -6. Aluminiums have to be +6 to counter it. But the problem is, I'll move it a little. But the problem is there are 2 aluminiums. So each individual aluminium has to be +3 because Al2 becomes +6. It's Al2 is equals to +6. Individual Al has to be a +3. So aluminium gets a charge of plus 3 oxidation number, or perhaps it's lost 3 electrons. Oxygen on the other hand is always a -2. It always gains 2 electrons. That's nothing new. For more examples, let's see Cu2O. I know it's a copper oxide, but I'm not sure about the charge. I'm not sure about the oxidation number of copper. I know for oxygen it's obviously a -2. It's a single oxygen over here, so it's a -2. Copper has to be +2. But I can very simply see this. Okay, it's not copper, it's copper 2. Copper 2 is a +2 over here. So a single copper has to be a simple +1. So copper individually is a +1. Oxygen, like always, is a -2. So it is actually a copper with a charge of +1 oxide. We can obviously write the oxidation number in brackets while we are talking about the names. So far we have seen that we can find the oxidation numbers. Let's try out few more examples, but with polyatomic ions. Just to revise what polyatomic ions were, we should see that polyatomic ions include nitrate, it includes sulfate, it includes a carbonate, it includes a hydroxide. These are the common ones. Let's try out. Let's try their names first. We should know that it's a nitrate, it is a sulfate, the CO3 is known as a carbonate, and the OH1 is known as a hydroxide. So let's see. For example, if you have an element, let's call it element X, which is with NO3 twice. It's not NO3, it's NO3 twice. There are 2 nitrates over here. So you would know that individually a nitrate is -1, but 2 nitrate means it's a -2. The X has to be +2. So the oxidation number of X is equals to +2. Let's start one more example. Let's call it element Y, which is with a sulfate. I know that individually a sulfate is -2. SO4 as a combined product is -2. Y has to be +2. So the oxidation number of Y turns out to be +2. It's one Y, it's just a single Y. We don't have to worry about how many Y's are here. For more examples, let's see. If it is Z, which reacts like this, so I know that a single CO3 as a whole is a charge of -2. Z has to be +2 to counter it. But sir, we can see it's not just Z, it's a Z2 which is +2 you're saying, because it has to counter the carbonate now. Individually a Z is going to be equal to +1. So we always quote the number for a single element, a single atom. So the oxidation number is +1. Even if it counters because of the 2 Z's, individually the oxidation number is equals to +1. A similar example would be, for instance, let's call it element Q. Let's say QOH3. So I know that OH as a whole is a -1. There are 3 OHs, which means a -3. Q has to be +3 to counter it, so Q has to be +3. So the oxidation number of Q is going to be equal to +3. So this is how we find the oxidation number of individual atoms. If it's a single pure element, it's a 0. If it has a charge on it, then it's not a question. Within a compound, you have to find out what is the oxidation number of one side, and then you can find the oxidation of the other side. Few of the common oxidation numbers you have to remember. For example, Cl's, Brs, the group 7 ones are always -1. Oxygen is always -2. Oxygen is the most common one over here. So oxygen is always a -2. And then nitrate, sulfate, carbonate, hydroxide, these are -1, -2, -2 again, and -1. So these have to be remembered. In the next video, we'll combine these ideas to see how the equation actually works. So the next video is gonna be redox reaction using the ions. So stay tuned, guys.